So, hello everybody, and today we are going to continue discussing our signals theory. And what we now want to discuss is, if you recall, last week we discussed that we can split your signal into multiple components, and any shape imaginable can actually, you can do that for that easily, quite easily. However, um, in most traditional signals theory books, courses, etc., they usually start with something like integral Fourier transform. So they first go from continuous signal, discuss a lot of mathematical formulas, calculus, and only then they go to the digital signals. And in my experience, from when I was reading this for local students, it's actually much easier to understand the opposite way around. First, we take digital form, where all the integrals are replaced by a regular summation, the concept itself becomes quite much easier to understand. And once you know this stuff, then we can move to integral form and check what happens to continuous signals. So because of that, before that we start actually speaking about it, let's discuss about digital signals and how to create ones from continuous signals. Well, kind of, we have mentioned this already, that you have some continuous function like this, which you then sample by making certain readings with specific fixed period, and then accordingly process these samples as a signal. Now, this has actually quite a lot of benefits. Let's start with as simple as that digital signals are universal. It doesn't matter anymore if it's sound, if it's video, if it's pressure, light, I don't know what else, uh, acoustic wave, electromagnetic wave, all of that can be converted into digital samples, which essentially are just numbers for your computer, and your computer doesn't have to care where these numbers come from. All that it needs to do is to add, multiply, subtract, do basic stuff with these numbers. So essentially that means that a lot of quite specific mechanisms like gearbox mechanisms or some pressure sensors or analog electrical circuits can be replaced by a processor, which then runs some code. And if you suddenly decide that your processor should do something different rather than simulate these cogs of clock, then you just rewrite the code and it starts doing different stuff, which is very amazing, which is not very nice. Also, most of mechanical parts, let's be honest, are not how we can say, not eternal. Yes, they wear and break with time. Also, temperature affects their dimension. Then you need to service them, do a lot of stuff. It's much easier with a computer also in that regard, because 2 plus 2 in a computer doesn't really depend on what is weather outside and when was the last maintenance for your computer, etc., etc. It either works or doesn't work, as simple as that. It's not like the result might change because of some conditions. So that is one big, huge benefit for us. Also, next question is how then we should describe this signal. In fact, this is a digital signal because I use MATLAB to generate it, plotted it, and saved the screenshot to put in the presentation. So in its nature, it was already created inside of computer memory. So what exactly is the signal? How we describe it? We discussed last lecture that we can say that, for example, if I wish to describe a rectangular shaped signal with more or less accuracy, I can go this way, like saying that my rectangular shape is sin of double p t plus 1 versus 3 sin 6 p t plus 1 versus 5 sin 10 p t, and all the way as long as I'm, as I want to. So all the way up to infinity. So this is actually valid formula which you can use to create a, well, if you take enough of them, you can create a perfect rectangular shape. Now, how about this signal? How should we describe this as a formula? Well, the good news and bad news are the same, that we can't and we don't have to. Yeah, so for us, this signal is rather a sequence of numbers, just samples and nothing else. Yes, so that essentially we don't really need to know any kind of formula, no matter how complex or simple it is. It's just these numbers that are interesting for us. And then having these numbers, we actually have quite a lot of tools like machine learning and all the other stuffs to approximate whatever formula we like to. Yes, so that again is very convenient for us. Hence, we represent signal in the form of array. It can be one-dimensional array, multi-dimensional array if necessary, and that is it. Yes, it's no longer tied in any way to its physical nature as well. For us, these are just numbers. Well, again, if we make some very specific processing, we might want to care about where these numbers come from. Like, if we say measure I don't know, mass of objects, then we know that numbers cannot really be negative because negative mass doesn't exist, yes? But these are more like an interpretation of results rather than calculating this stuff itself. Now, let's take for simplicity just a very simple problem of, let's say you have some continuous analog signal, and for this analog signal, what you want to do is to find out its DC component, its average value. So normally, by formula, you would have to know what is the formula of this signal to be able to put it inside this integral. Yeah, so otherwise you cannot really integrate it on paper, at least, yes? So you need not only actually to do this stuff, yes, to count the integral, but also we need to know what to put inside of this integral to calculate this average value accurately. So it goes in range from a to b divided by the interval and itself. Now, to the contrast, in the digital case, we don't need to know the formula, and we also don't need to calculate integral. Yes, all that we have to do is to add all of these points, which are numbers, together into one bigger number, and then divide them by how many numbers you have. So a really simple average value to be calculated, yes? And there is a lot of these stuffs. Even Fourier transform itself, how to calculate spectrum, is then becoming as simple as that compared to having to deal with analytical formulas, integrals, tables, and uh, I don't know, and sometimes you might come up upon integral which you cannot integrate on paper, and you have to resolve to numerical methods anyway. So essentially, it's much easier. Now let's have another example. Since I'm more from telecom, I show some examples here and then related to that, but it also works for computer networks, I suppose, as well, Wi-Fi networks and all that stuff. So let's see what happens if we want to try and transmit over some distance analog signal and digital signal, how this situation changes. Now, what you need to know about the channel where this transmission is happening is that it essentially does two bad things for us. First is that it introduces loss to your signal. Yeah, so the signal is attenuated. So if it had, let's say, for example, 100 watts power on the input, then at the output you are going to get, depending on where are you located. Yes, so here you have distance, here you have power, so your power over a distance is going to decrease. That makes sense. The further you are from base station, the weaker signal becomes. The further you are from Wi-Fi router, the weaker signal becomes. The weaker signal becomes, the more difficult it is to receive it, the lower is your data speed, and a lot of bad stuff happens. That is the first problem, which on its own might not be a big problem at all for us, if not for the second problem, the noise. Noise is a very, very weak, constant signal background that's barely doing anything to your signal normally if you are located here. However, once your distance is quite large and signal has traveled it and lost its power, then noise starts to kick in and do some real damage to your signal. So that is the problem why your signal becomes weak, because now noise can do something bad to it. And together with that, that leads to error, refuses of connections, and all that stuff. Inability to even see a network, yes, that you are way too far away from it, and so forth. So we'll consider that your loss is some number g, which is less than 1. And of course, the receiver, when it receives this signal, cannot really work with very, very weak signals. It has to compensate for this loss by amplifying. So you have some amplifier which is reverse of your G. Yes, so accordingly more than 1. So let's see how then transmission happens in that situation. Let's suppose that is our original signal that we want to transmit. It's an analog signal. Let's say it's a fragment of speech, of music, or something that you cannot really change anything in it. Otherwise, it's going to start sounding differently than it was. And it may lose meaning if it were words, what it was containing as information. So that signal is located at the transmitter output here. That's what we see right now, is how strong is that signal is. Now we send it to channel where it's going to take propagation loss and start decrease in its power. So what will happen then at this receiver point is this signal will become much weaker version of itself, like so. Now, as I said, noise is a very weak signal that will not do any damage to this signal, yes, because, well, noise looks somehow like really like this, yes. And if it happens to add on top of this signal, well, it's not a big deal. Now, if this noise adds on top of this signal, the effect is much more destructive, yes. Although, from the first look of eye, it doesn't make seem so, because it's very weak also, you need to realize that now at this point, weakened and noisy signal gets to the receiver, to the antenna, and amplifier that is going to boost power by adding the gain not only to the signal, well, essential to the signal that it sees, but the problem is your signal includes noise as well, which means noise is also going to get boosted. There is no way for you to separate them, and as of such, your signal become noisier version, which again might not sound so awfully if you were to listen to it, a little bit static in the background and otherwise would be fine. So where is the problem? Let's say we want to cover a lot more distance from London, let's say, to New York, over the ocean. Yes, now in that case, if we were to send the signal, no chance that it will arrive to this point in any way that you will be able to even determine that it somewhere existed. Yes, so you will hear just noise here at this point. So we need to do something about it, somehow to, in a sense, refuel the signals as it goes during the transmission. So for that reason, we use a device called repeater. And this is something you might want to use if you're, I don't know, if you have some big house, yes, and your Wi-Fi signal is not strong enough in certain parts of it, then you put some repeaters, which then repeat your signal in those problematic places. So basically, the idea is quite simple. You receive signal, you amplify it, send it further. Next in the chain receives, amplifier, sends it further. Now, this way, we could actually like cover a lot more distance, at least in theory, because, well, we can repeat this as many times as we need to. Of course, in this situation, it's difficult because it's on the bottom of the ocean, but still manageable, still possible to provide some power source. Maybe, you use some very high quality cables because, well, right now we speak about not optical fiber, but regular copper wire cables, well, of high quality, etc., shielding, blah, blah, blah. But still, eventually, even for those cables, sooner or later, there will be some maximum distance after which they cannot be used anymore without repeater. So anyway, we optimize the cables, we put as small number of repeaters as we possibly can to get it working. But where's the problem here? Now, we already know how our first received signal looks like after the first repeater. So you receive signal, you amplify, amplification also increases noise. It is being sent further in the channel, and the gain is attenuated, received by repeater, amplified, sent further. So this is how it looks after the second repeater. Now, if you look closely, you will probably slightly notice that there is a little bit more noise than it was, and it is in fact so. Now, after the third repeater, noise continues to accumulate, and it's not difficult to see the more repeaters you are going to have, the more noise each of them is going to introduce, and at a certain point your signal will become too noisy to work with, and well, even this approach doesn't seem to work. Now that is the problem of analog signal, because we cannot clean it out the noise, because we don't really want to lose any details about the signal. The digital signals, however, are somewhat easier to work with at this point, because there is no such high variability in itself. It's either 1 or 0 in a sense, which is much easier to work with. Yes, so let's say now when we want to send this in a digital form in modern world, we convert it into digital form, then we use optical fiber, which still will, over such long distance, require some regenerators to be used, but anyway, we'll see the effect. Yeah? So as we discussed previously, the conversion of analog to digital happens in two steps. First, you do samples. So your line, red colored line, is your original signal, which you sample and take readings from. The second step, yes, so first is sampling. The second step is quantization. Essentially, you round values to the closest of these quantized levels. Yes, so you see that this red line was in the middle in between these two black lines, two levels, and the closer one was this bottom line, which was rounded too. Yeah, so basically it's regular rounding effort. You lose some of accuracy of the signals by doing so, yes, but still it's, if you have enough of these levels, it's good enough. Now, what is important to mention here is now that each level also has a binary code word assigned to it. So essentially, for example, now this point means that instead of specific voltage level, which was I don't know how much, maybe something like 1 point some minus 1 point something volts, 1.3 or something like that, you are going to send binary code word 111. And for each of these symbols, ones and zeros, you assign voltage levels like 5 volts and minus 5 volts, for example. Meaning that your signal is now, all of these samples are going to be converted into rectangular shaped pulses, like so. Yes? And with this signal, it's much easier to deal with noise. Also, we still have to use regenerators, just to be fair in this comparison, yes, so we will use regenerator also. And the regenerator actually is a little bit different from the repeater. The regenerator can clean noise. That is a big deal here, because physically nothing changes. The signal is still going to be suppressed, it's still going to be affected by noise. Your receiver is still going to receive and amplify noise and your signal together. But now, since we know for certain that the only possible outputs of your signal can be either plus 5 volts or minus 5 volts, we can clean this signal out of noise. As simple as to compare with 0. So if the number is positive, then it is plus 5 volts. If it is negative, then it is minus 5 volts. Or by calculating the average over this distance, which is also going to work. So we have multiple methods to do so. Essentially, what that means for us is that once we do so, the regenerator is going to send this signal to the next regenerator, and it's going to repeat again. So no matter how many regenerators you have, each of them will be able to clean this out of noise, and it works. Well, of course, this will introduce extra delay because each regenerator will still have some time to work with your signal, so you still want to reduce their number, but essentially, technically, if you put them over a safe distance where you just don't allow signal to become too weak for the noise to become not like this, but somehow like maybe somehow like this, which is also possible. It's just like you put your regenerator too late. Yes, the regenerator cannot help you here anymore. You need to reduce the distance to make it possible to filter it. But either way, hopefully this demonstrates that actually smart approach to this problem can solve it, which for analog signals otherwise could not be solved. So now let's go further about how exactly this sampling happens. Yes, consider here you have your analog continuous uninterrupted signal, and what we want to do now is to convert it into samples and essentially just take readings of this signal with a certain regular period of t samples, yes, TB, discretization. Now, mathematically, this would basically be as simple as multiplying your original signal here with this comb of very short, strong pulses. So each of these pulses is going to be multiplied by a signal. In between the pulses, there is zero. Zero multiplied by signals produce zero, and essentially you end up with this signal, yes, which is now sampled version of the signal. So here you can see the bigger picture of this. Yes, we take readings. We don't do anything about amplitude at this point because we deal only about discrete signal at this point. Yes, digital signal will have quanting applied to it as well. Now, there are multiple ways to go around it. For example, here you can see that we have fixed steps. So this step is constant and doesn't really change. The signals can be different. Some signals may look like this, yes, so like this. And obviously, fixed step would not work well there. You would be interested to have somewhat bigger step at this point, and once you get to this point, you will want to go a little bit faster. Now, of course, this is optimal approach, but still this produces a lot of problems. Mainly, the main problem is that your receiving device doesn't necessarily know when it has to take large step and when it has to take small step. Yes, that's not exactly clear, at least not obviously clear. Yes, so because of that, in practice, we usually prefer just to go with a smaller step for the entire of the signal, just to be knowing that your next sample is supposed to be arrived at guaranteed time, which you are expecting it to get, and basically not to deal with this uncertainty, like now my period is higher or smaller, yes? But I digress a little bit, so for us, we will consider it only as a fixed interval. That's also a case for the processor systems, for digital devices, when you have more or less fixed clock time interval, yes. Now your commands might take different number of clock intervals, but the clock time interval itself is like well, more or less fixed and maxed out usually for the processors we are working with. Now there are two questions now we have arising out of this situation. Yes. Well, first of all, is there a way to choose a proper sampling time interval? Because obviously we may choose it incorrectly, and that may have some problems, may not. We also don't exactly know that, yes, right now. So, and the second question, if there is any fundamental limit, minimum, that you have to choose if you want to for the system to work okay, because obviously, well, I have this signal, and if I were just to choose one sample, like so, it would not be enough to be able to reconstruct from this point this entire signal afterwards. Yes, that is the problem, is that whenever you do this sampling, like so, from the real signal, your continuous line is gone, like so, and you are left just with these samples. And it depends if you will be able to reconstruct this original line or not from these samples entirely on if you have sufficient number of these samples, if you have enough of them to be able to do so. But even so, that doesn't mean you have to read it as often as possible, or even as impossible, because once again, we return back to this point, and I say it again, that each of these samples is going to be represented by some binary code word, meaning the more samples you have, the more bits you need to store, transfer, work with, etc., etc. So this essentially becomes time problem, that you are going to need time for everything of this, and computational power too. So we also don't really want to overdo it as well. So what is the optimum? What is the balance here? Now, once again, I pointed it out that is very important that all that was in between the samples that you have saved will be lost forever. Yes, and there is no way for you to read it back somehow, except that get it out from your samples that you have. Yes, so basically, if you have enough of the samples, it is still possible to reconstruct it. Yes, so now we have lost all the information between samples, but in this particular situation, it's not permanently lost. Yes, it's still possible to recover it back based on these points. Now that is a good for us, because effectively that means we have some kind of compression here, yes, that allows you to reduce amount of data to work with, process the most important and significant points. Once you have done them, reconstruct signal back to the continuous line, and I don't know, play back that on the speaker, for example. Now the reconstruction, contrary to the intuition, is performed not by connecting these straight lines like so. It's not as simple as that. Because let's be honest, if you do reconstruction like that, you are going to lose some information as well. Specifically, for example, here. Yes? So original signal was going like this curved shape. It decreased, that started, it increased, and decreases, and started increasing, and it was not monotone at all. Now, if you just connect with a straight line, well, your signal is going to be not so accurate as before. Now, you may object that we just need to read more samples, then our line is going to approach this line. True, but also unnecessary, because we are going to connect these points with a different approach. We are going to use this type of a function, which is called sync function, sin x versus x type of a function. It's a remarkable limit, yes, as you know from higher mathematics, which when x approaches 0 is equal to 1, which is exactly this point here, yes, because, well, if your time t is 0, yes, then accordingly you are at this point at the beginning. It's also remarkable in a sense that it produces, well, it not produces, it crosses 0 at specific points here and here and here and here and here. And it just happens so that at those specific points are going to be our samples, other samples. So as you can see here, I now have replaced this one sample with this entire function. Let me try to make it more observable for you. Well, I tried. And, well, it goes through 1 here, precisely through your sample ladder, And also in all the other places here it goes through 0, all goes through 0, so it does not contribute anything to these samples, but creates some space in between, so it creates some line connecting these. Now what you are going to do is to repeat the same procedure for each of these. Now you will have a lot of this line interfering with each other, and if you were to add them together, for example, you add this line, you add this line, and this point then accordingly is going to end up somewhere around here, which is going to produce this effect of this curved line, smooth, non-monotonic line, like so. And if you add all these lines together, you are going to get perfect reconstruction of your signal, even with a limited number of samples. So what we can conclude from this is that ideal reconstruction is still possible if you have sufficient number of these samples. So now the next question is, what is considered to be sufficient amount of these samples? How many do you need to take to be able to guarantee that it will be possible? Now, for the sake of example, let us take one single rectangular pulse of duration of 50 nanoseconds. During the last lecture, I explained to you that we can actually consider this rectangular pulse shape, single pulse, as the extreme case of periodical signal when you have period lasting for infinity. And as you increase this period by keeping the same pulse, your spectrum, which originally for rectangular shape periodical signal was like so, yes, so the spectrum was like so, is starting to produce extra samples in between like this. And like this. All the way until it's creating this sin X versus X type line, which you can observe here. Yes? So now we see here frequency on the x-axis, yes, and well, we want to decide where are we going to put some limit. And why we want to do that? Well, because the condition for you to guarantee that you will be able to recover your signal points perfectly ideal is to choose the sampling frequency, the frequency, how often do you take readings, to be minimum of double maximum frequency of your spectrum component. So as we know, theoretically, our rectangular shaped pulse is has infinite amount of components, but they also, as you can see from this picture, become less and less significant. Yes, so at this point we can say, okay, we will consider maybe 100 megahertz where it still matters, and after this point, honestly, their total contribution is just too small. So from that perspective, we say that maximum frequency here is 100 megahertz, yes, for um, 10 nanoseconds pulse, meaning that your sampling frequency should be at least double of this number, 200 megahertz. Now, if we try to calculate the period, then that's going to be 1 versus 200 megahertz, which is essentially 0.005. Sorry, it's 50 nanoseconds, not 10. I'm a little bit confused because of that. So that means that for this pulse of duration of 50 nanoseconds, you have to take one sample once per 5 nanoseconds. So effectively, that means you are going to have 10 samples of this pulse, which is still over what is absolutely necessary, much more than necessary, yes? But we have been deciding it based on this choice of maximum frequency because to some extent it depends on our decision. What is this maximum frequency? We have to choose it, yes, based on some conditions. For example, considering that their total energy is like 5% of your signal, or maybe some other criteria. Now, is it safe to say that if, for example, I were to decide that my limit here, I would be fine? Well, from the perspective of the being to able to reconstruct it, yes, but there will be some other very unpleasant effect coming into play called aliasing. If you ever have had work with some graphics or even computer games with bad hardware, then you might know how exactly that looks like. And that is the problem of digital conversion, yes, about not sufficient resolution and all that stuff. But we'll get to that soon enough. At this point, let's go through like this. We say this is our maximum frequency according to the sampling theorem, Nyquist criterion, yes. We have to choose then at least 200 megahertz minimum. We can choose more if we want to, but not necessary, yes. But if you choose less, then sadly, you will not be able to recover that kind of signal, yes. Now, the question is now what happens to the spectrum. So this is a spectrum for your original, not sampled signal. So again, let me draw it like this, rectangular closed shape. Now I do sampling from this signal. And the spectrum you see here right now is for the black line. Yes, so black line has this spectrum. Now I want to know what will be spectrum for these purple samples. And it turns out it will look somehow like this. What happens here is, well, for that to understand, we need to really focus first on some fragment of it. Yes? Uh, can I? Well, I'm going to do it like this one. So let's focus on this 100 megahertz band first, this part. Well, if we compare for the discrete signal, how this part looks like, and for the original signal, it's the same. Yes, so basically, this part is the same and nothing has changed here. What happens further, though, is different story. Yes, now you can see that actually here, it's probably easier just to redraw it. The second part of the spectrum is oddly resembling the first one. And in fact, it is a mirror of this spectrum versus frequency, which is called Nyquist frequency. Or this is 1/2 of the sampling frequency. So all the way from the frequency to from 0 to 100, we have our original spectrum. From 100 to 200, we have a mirrored copy of this original spectrum. And from 200 up to the 400, the process cyclically repeats. Yes, so the spectrum is periodical actually for discrete signal. Now, that's a mathematical abstraction difficult to understand, but this just means that your discrete samples actually require very, very wide spectrum. And in reality, because of that, of course, in our computers, we don't necessarily have these pulses as short as infinity. They are always some nanoseconds, some picoseconds, but either way, very short pulses, which allows you to cut down the spectrum a little bit, yes? Because otherwise, you wouldn't just have enough good enough cable to connect your CPU to your RAM or any kind of other conductor on the motherboard, yes, for this to work good enough. Yes, so because of that, we make some limited time duration pulses. This stands for the so-called delta function. Delta function is yet another mathematical abstraction that has the following properties. So its duration, tau, is zero. So it's like zero duration. Yes, very short. Its amplitude, u, is infinity. So it's also infinitely strong. And its area, so that is integral of this delta function, is 1. Well, because you multiply, in a sense, you consider this as a rectangle, yes, with a height of infinity and width of the 0, and you get uncertainty, which results in 1, yes. So this is mathematical abstraction, of course. In reality, we always have some measurable units, something like 1, for example, with a certain duration, very short, although still not momentarily, etc., etc. Now, seeing how this spectrum repeats over and over, we can get an idea of trying to print it out on the sheet of paper and wrap it into the tube. Yes, and that's actually what we can do about it. But yes, we can do about it. But we'll speak of this, I suppose, some other day because that's a separate topic. This is called Z transform. Yes, so for Z transform, well, actually, I can show you this example. I have it. Slightly different version for telecom theory, and I was recently showing it. So you think of it as wrapping this entire spectrum in a circle because it's going to infinitely repeat over and over and over each 200 of megahertz all the way up till this point. Yes, so and this procedure is called Z transform. We'll definitely have a course on that, lecture and practical exercise, because this is a very convenient tool to design some digital filters whenever you need to somehow filter your data, images, whatever. Yes, we'll actually well mention filters today also. Yes, that's when you have to resort to the Z transform. Yes, and you can see that actually Z transform repeats this part of the spectrum all the way up to the first half of the circle here. You can even see that this amplitude start decreasing. Then this part here, not on this one, but this one, is next half of the circle. And after that point, it starts to repeat over and over and over again. So you map this spectrum into complex Z plane, which allows you to do, well, we'll learn about what it allows you to do, but many stuff can be done much simpler than in a time domain, much simpler even than maybe in the frequency domain of Fourier transform. Okay, but usually, of course, when we say we want to display a spectrum of discrete signal, we don't really draw that much of these components. We either draw the full spectrum all the way up to sampling frequency, which in my case is 200, which has your original spectrum and the mirror. Well, this is kind of the same, yes. Because of that, it's very common to actually display the spectrum only up to the half of the sampling frequency, or so-called Nyquist frequency, which shows you the spectrum of your original analog continuous signal. Yes, that's usually what we do. Now, let's consider two scenarios. One scenario is you take readings more often than necessary. Another scenario is you take readings not so often as necessary, and as of such, what may happen. So first case can be called oversampling. Yes, you take readings more often than necessary. That's usual technique we are going to use in our practical exercises to demonstrate a very smooth and nice line by simply oversampling otherwise, separate points that cannot form a smooth line. But apart rather than that, rather than for visualization, I don't really see much point in this oversampling, especially in tasks like computer networks or computations, etc., because this is going to cost you more computational time, more transmission time, more resources, etc. Yes, so basically, without giving you anything in return, that's most important. You may think that this may increase accuracy of recovery, but no, as I have said, you can perfectly reconstruct the signal from the red points alone. There is no need to take extra black colored points just, for something. It's just going to increase amount of numbers you will have to deal with. Yes. Now, if we take, however, lower frequency than necessary, that is a problem. Yes, because right now these black colored points cannot be used to reconstruct your original blue line signal. In case you will try to do so, you are going to end up with this kind of a signal, which is also harmonic and in fact closely related to this original signal, but it's still some other signal. Now this is exactly Elias effect, yes? What's that? So here we have the spectrum, here we have selected some maximum frequency, which is our Nyquist frequency, or the half of sampling frequency. Here we have accordingly full sampling frequency. And what we did right now is we decided to use sampling frequency in such a way that the half of this sampling frequency is lower than this signal itself, meaning that the spectrum of our signal is located here. Yes, that is the frequency of this blue line. Now, because the spectrum creates aliased copies, then it works in both directions, actually. Yes? So meaning that this will create copy here, just like this would create copy here as well. And essentially, because of that, we have received another signal with another frequency, much lower frequency, much slower signal, yes? Which is its mirror versus this F sampling. Now, knowing this fact and using some very advanced processing techniques can still actually be used to our benefit to be able to recover this signal because, well, essentially, here you had frequency of the signal, let's consider this F, and the frequency of this signal was F sampling minus F. So they are still related, and it's still kind of possible to recover your original signal even in such situation. But again, this is very difficult, and let's be honest, you will most commonly use signals consisting of multiple components. And once they start overlapping with each other, then there is no point going back. Yes, then you will have irreversible damage to your signal. Now let's see this sampling effect on some kind of experiment or visualization. So here you will see some video fragment. Let's now actually open this link. Let me pause it while it's loading. Let's also make the screen larger. So what you can see here, also I believe I have playback speed reduced, so let's put it to normal. It is normal, yes. So what we have in this experiment is this wheel rotating by being connected to the motor. So you have DC motor which rotates this wheel, which you can observe. And the motor is connected to the power source, which you can adjust. So you can increase the speed or decrease the speed of rotation. Now, I will tell you at once that during this experiment, the speed will always be increasing. So you constantly increase speed more and more and more, making it to rotate faster. Now, what does this have to do with today's topic? It has to do with the fact that you are now watching the video record, which was captured by a camera. And the camera makes samples, for example, 60 frames per second. That is the discrete device, which makes readings of your reality, what it sees, yes, 60 times per second. And if it happens just so that your wheel is rotating a little bit faster than what it can capture, then it will see funny things, let's say like that. Let's just demonstrate you. So the idea is quite simple. Now we are going to see if our camera has some limit in being able to see how fast this rotates and what this can lead to. For that experiment, now you can see we always rotate counterclockwise. Yes, we also have this red tape here to be able to see the true rotation direction when we will not be able to tell that from these white ones. You will see there will be some point where these white lines will just stand still and your red one will be rotating. Or even more so, it will suddenly start rotating in opposite direction, although in reality it does not, yes? This is the effect of camera limitation. If you were to have not 60 frames per second camera, but 120 frames per second camera, it would be normal, yes? So that's problem of undersampling. So see, it increases voltage and it starts rotating faster. Now it's rotating clockwise. White ones, yes, red line is proper. Now it's stopping. Now it's stopped and starts rotating again. Other way. Does your wheel actually rotate in different direction? No, it still rotates counterclockwise, but it's constantly getting these changes. Now, why is it happening and how we can relate that to this picture of spectrum we were having just now? So let me actually reduce the speed and go through the spectrum we had. So that would be, well, actually, I will use that one, which is a little bit even more friendly. Yes. Let me try to somehow put them together. Or maybe I'll just draw on top, yes, the same one. So we have here the spectrum all the way up to F sampling versus 2. Then it mirrors all the way up to F sampling. And now, by analyzing how exactly this wheel rotates, I'm going to tell where exactly are we right now. So now you see that the person is, so all of them are rotating, yes, counterclockwise, red and white alike. Now the person takes these controls and increases the voltage, making it rotate faster. Then it picks its camera from the top view and continues to rotate this control, yes, by increasing the rotation speed faster and faster. So now you see that it rotates counterclockwise and suddenly it's not, yes? It's just like that. Counterclockwise and clockwise. Without any, transition, without any warning, without anything. What happened here is that we actually increase the speed at which our wheel rotates all the way from 0 up to the F sampling by half. So that was this point, F sampling by half, when it was rotating And you also, if we were not making it slow mode, yes, would notice that it was the fastest effect visually how it rotated. Now at this point, it's changed the direction and will start to decrease rotation speed all the way up to stopping completely at sampling frequency. So let's see how that happens. Yes, so now it rotates maximally fast. The red line is still showing the proper rotation direction, although, yes. Now, next slide will explain why it happens so for red line and for white lines not. So now you can see that it actually starts to slowing down, meaning that we approach to the sampling frequency here, and it's going to eventually stop while red line is still rotating as usually, nothing changes there, yes. And it stops all the way to the frequency 0, which is the same as f sampling, and starting from the frequency 0, it starts slowly rotating in the other direction, yes? So the process starts to repeat. And as the person rotates this knob more and more, it constantly increases speed, but it just goes forth and changes direction by passing half of the sampling frequency and full sampling frequency, which in our cases is 30 FPS here and 60 FPS here. Okay, so with that in mind, this demonstrates this so-called wagon wheel effect, which you may observe into some older movies, especially in older movies when the cameras were not 60 frames per second and even slower, when your wagon wheels were actually rotating in different directions than it's supposed to. Now here, there is another video link, which I'm not sure if it works, and we are slowly getting to the end of our today's lecture. But you can study this yourself. I'm just going to explain the idea now. So now the idea is that here you can see, well, okay, let's maybe turn it on just to see some examples. I can explain these examples, with the video open, not a problem. Let me just change back the playback speed. So what we have here now is multiple wheels with different amounts of these lines. Yes, here you can see 2 lines, 3 lines, 4 lines, and different angle in between them. So here you have 180 degrees, here you have 120, 90 degrees, 72, etc., etc. And here the person specifies rotation speed in degrees per second. Yes, so essentially, for example, if you specify, I don't know, some small value, they all rotate equally, yes? But if you specify any number, which we see here, for example, 72, it will make this wheel stop in place because between two frames, there is exactly 72 grays rotation, and the distance between them is also 72. Well, it specified 60, yes? You can see it's 10 still. Now, if you make it 61, it's going to rotate opposite direction. If you make it 59, here it's rotating counterclockwise, here it's rotating clockwise. So exactly like so, because the fact is that between frames happens the following. Yes, so we have this wheel here. Now, next frame is going to rotate 61 degree, meaning that it's going to end up here. This one is 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 going to end up here. And what you will see is that it not rotated this direction, it rotated smaller angle here. Yes, for camera, it doesn't know. Yes, it sees one picture is like so, and another is slightly rotated in this direction because it made a little bit more than the 60 degrees. And other ones, wheels, do not suffer from this effect either. Yes, because they have different combination of these patterns. Yes, so that allows you to actually see that rotation is happening in proper direction. Indeed, it's just this specific situation that between two frames, actually it was just capturing the difference, and this difference seems like it's rotation in different direction. That's the problem of this aliasing effect. Yes, that's uh, wrong choice of the sampling frequency. Now, aliasing effects also works in graphics. So if you happen to work in 3D modeling, animations, drawing, yes, etc., you probably know that if you work with raster graphics with pixels and you zoom too much, then they become these square pixels. If you have not high enough resolution of your image file, then it's going to look jaggy, like so, because, well, you sample this original shape, which is red line, that is your original picture, and these blue, or not blue, but gray squares are basically those pixels where it hits on top of this line for at least 50%, let's say like that. Yes, and you can see that these pixels not necessarily form the accurate shape. How you can improve that? Two ways. First, increase the resolution. Yes, so if you have smaller pixels and more of them, your shape is going to become more accurate. Now, not always that is possible, especially if you start with this picture, then there is no way from this picture to get this picture again without, advanced processing, artificial intelligence, and even so, it's not going necessarily to be as accurate as to go back to your source picture and scan it with higher resolution. But there is also a way how to, make these edges a little bit more friendly, like using something called anti-aliasing filtering. Yes, anti-aliasing filtering. Here you can see, for example, yes, these jagged effects and different kinds of anti-aliasing filters that solve this issue for you. Here you can see that this is aliased line. Now on the projector, probably it may be a little bit difficult to see, but let me try to zoom. It's a little bit jaggy around the edges here, yes? Whereas aliased version is very smooth and soft line. Why? Because it has not only black and white, like here, yes, but also different gradations, some shades in between, yes? And here also you can see that. The idea how to do that is actually pretty simple and very easy. Yes, let's say, for example, this pixel. How was it calculated? Well, you take this pixel and all the neighbors around it and find the average intensity of the color in all the eight pixels, and assign this average color to this pixel. Yes, so that's how the averaging low frequency filter, anti-aliasing filter actually works. But this is very basic approach. Yes, there are much more technologies. Even if you open some kind of computer game and go to graphics settings, you will see at least, I don't know, 3 or 4 types of these anti-aliasing filter options. Each of them works slightly differently, yes, and asks more resources or less resources and so on. So this is actually a big deal, yes, because we are dealing with a discrete process represented by separate pixels. That's how our monitors show, yes. Of course, you can buy 4K monitor, but then you will have to change computer maybe as well because of that, and so on and so on, yes. But signal processing in some cases, even for 4K, yes, there will be still some situation when it might happen still, yes. So signal processing, which we are going to learn in this course, is going to be your help here. Now, this concludes our introduction to the digital signals. On Wednesday, we will have some practical exercise, some experiments, so be sure to bring your laptops if you want to with MATLAB or cloud access to MATLAB. And then accordingly, we will try to do some stuff like making some signal, getting its spectrum, maybe filtering it, seeing how it reconstructs, and all that stuff. Okay, that concludes today's lecture. Thank you. If you have any questions, don't hesitate to ask, email. So see you then soon.